Okay, so this is the first video in a series of videos where we will be going through chapter 4, which will be covering proofs and different types of proofs. Okay, so we're going to be starting and talking about direct proofs. So the first 4 lectures, so to speak, will be covering direct proofs, and then we will move on to indirect proofs. Okay, so this is how we're going to begin. So direct proof and counterexamples, number 1. This is just an introduction to this section of the course. So this over here, so let's go down. So our first definition here, in which we will be targeting direct proofs, right? So in order to evaluate the truth or falsity of a statement, we must first understand what the statement is about. That is very, very important. It's the very first step of writing proofs in this section of the course. It must be written in such a way that it relates to the statement that we are speaking about. If we are asked to prove something and we prove something different from what we are asked in our statement, then our proof is obviously wrong, right? However, that comes with a caveat, and that is that if we are asked to prove something and then we prove the opposite of it, right? Then that is something to some extent is called the proof by contradiction, which we will get to at some point, right? So that is the only time that that works, right? But in most cases, we'll be doing the direct proof, okay? So we must know the meanings of all the terms that occur in the statement. That is obvious. Mathematicians define terms very carefully and precisely and consider it important to learn definitions virtually word for word. So you see this opening statement? If we can replicate the proofs in this section of the course, which is very big, word for word, then we will be more than okay, right? We'll be 100%, we'll be fine. And this is what is usually awarded total marks for. It must be done in a certain manner, right? And your language here is, you have to be very, very careful with the words that you choose to use and your sentence construction. Just as we had in the first part of the course with our syllogisms and our predicates and our conclusions and stuff like that. In the same manner, we have to be very careful about the language that we use here. Okay, so our first definition gives us here that n is even if and only if n equals twice the sum integer, and n is odd if and only if n is equal to twice some integer plus 1, right? And that is obvious because if I have an even number, let's just say an even integer, let's just say 2 or something like that, and I add 1 to it, right? Then it becomes 3, and that's odd, right? So this definition is obvious. Here are some examples. So is 0 even? Yes. 2 multiplied by 0 is 0. So that comes back here to my definition over here. N is even if and only if there exists an integer k such that n is equal to 2k. So these statements here are very important because as we move later in this section of the course, we are going to have to recall these definitions here and use them as facts, right? So yes, 0 is an even integer, is negative 301 odd, negative 301. Can we write it in this form here, 2k plus 1? Yes, we can. So that is fine. And here are some more examples. You can pause the video and check them out for yourself, right? But most of this is already known to most of you guys. So here's another important definition. An integer n is prime if and only if n is greater than 1 for all positive integers, R and S. If we have something new, n is equal to R multiplied by S, then either R or S is equal to n. Then we have the definition for composite here. An integer n is composite if and only if n is strictly greater than 1. the same function we have here, but we have a different restriction here for R and S. And formally, we write it like this here. N is prime if and only if there exists positive integers as such. And then, of course, we take the composite case and we restrict R and S here. So, is 1 prime? The answer here is no. A prime number is required to be greater than 1. So, we're coming back to our definitions here. So, these definitions must be learned word for word. Is every integer greater than 1 either prime or composite? Yes, right? Let n be any integer that is greater than 1. Consider all pairs of positive integers that are of this form here. Then there exists at least 2 such pairs. And these are the 2 pairs here, right? So we are going to use these definitions here to show these statements. Of course, C and D here are for your self-reading. You can pause the video and read. And now we're going to move on to how to construct certain proofs. Okay, so this section of the course is proof based. Okay, now I forgot to mention it at the beginning, which I really should have, and that is, let's write here. I really forgot to mention this. So it just occurred to me that we didn't actually define. So we keep saying proofs, right? So let me get my pen here. Right. So we keep saying the word proof. So P. But we really don't know what we are doing here. We know in terms of sentences what we are doing, right? We are taking some statement and then we are kind of showing that it is true, right? So we may have seen the word before called theorem. But we don't even know what a theorem is. So we can loosely define a theorem as a statement. So this is really a statement. So put it here. This is a statement. And this statement is true, right? This theorem here. So a theorem is a statement that can be shown to be true, right? Let's forget the method of how we show it to be true for now. Let's just take it at face value that whatever this theorem is, we can prove it to be true. So we reserve this word here, theorem, to really mean something that is very, very important, right? So let's put a star here by this. Something very, very important. Something that is less important than a theorem, but is still needed, is something called a proposition. Proposition. Okay, so a proposition really here is, to put it in a nutshell, is just a less important theorem, right? So a theorem is something that is true. It is a fact, right? Fact here, right? A proposition now is something that is not as important as a theorem, but we still need it, okay, depending on what we are studying. Okay, so we will have to show throughout this chapter and demonstrate that a theorem here is true, and we're going to do that by using proofs. So what is a proof now? So a proof really is a valid argument. This here is a valid, and we spoke about arguments at the beginning of the course. This is a valid argument that will establish the truth of this theorem here. That is what the proof, that is the whole objective of this proof here. Of course, how we do it is through direct proof in this course, of course, and indirect proofs as well. There are many other ways that we can do it, which is beyond the scope of the course, right? And we can even use certain statements that are true, right? Now, to use it to further demonstrate that these theorems are in fact true. And these things are called axioms, right? So these are statements that we assume to be true, right? For some real numbers or whatever the axioms may be. right? So this is our tree here, so to speak. So we go in a little bit more. So after a proposition, we have something that is a less important theorem, and this is something that is called a lemma, right? A lemma. So this lemma is just a less important theorem, but it's helpful, right? So this is something that is important as well to us. So when we have complicated proofs are really easier to understand when we have a series of lemmas, right? Which are true statements to prove this. So the lemmas back up the theorem here, right? So this is why lemmas are very important. So we can prove theorems using a series of different lemmas. So these are what we need. Of course, we have another one. There's something called a corollary. ROLLAY, right? So what is a corollary now? A corollary is a theorem. So a corollary is a type of theorem. We could say it is a theorem that can be established directly from a theorem that has already been proved, right? That is what a corollary is. So all of these things are interlinked over here. So we need to understand the scope of this, right? And then and then once we understand it, we understand where we are going. Of course, there's one more I left out. I don't need to really talk about it. Something called a conjecture, right? But that is right. We don't really need to study conjectures too much. We can know what it is. This is just a statement that we propose to be a true statement. A conjecture is something that we propose to be a true statement, but this has to be on the basis of some evidence that we have previously, right? And these evidences are usually taken from an expert in the field. So this is computer science. So some professor somewhere in the world will prove a conjecture, and he will say, or she will say, or they will say that this conjecture is true based on some previous work that they did, or some other scientist who has maybe proven conjectures before. So actually, we take the conjecture to be a true statement, right? We can't prove it, right? So based on some series of evidences, and then we arrive and we say, there's a step over here that we're not too sure about, but based on some evidence from some guy who has a lot of knowledge, right? We can take what he says and we arrive at this conjecture here. And we say, yes, it's true. Now, in the event that someone else comes along now, Professor M or L, whatever, and says, hey, I can prove this conjecture, right? And if they are successful in proving this conjecture, then this conjecture becomes a theorem. So we reach right back here at the top. If we can prove the conjecture is a theorem, then the conjecture become that's once we can prove that it's true, right? We could use a set of lemmas, corollaries, or whatever, right? So this is our branch over here, which we are going to conduct. If a conjecture remains, well, most conjectures, to be honest, end up not being true at all, right? They have some very rare cases where they end up being theorems in the end, right? So that was a long sidetrack from where we were. So let's get back to what we want to do, and that is construct some proofs, right? So we want to prove the following, that there exists an even integer n that can be written in two ways as the sum of two prime numbers. So this is one way using a direct proof. We let n be equal to 10 because it's an even integer. Then 10 is equal to what? 5 plus 5, which is the same thing as 3 plus 7. And 3, 5, and 7 are all prime numbers. So this is true. So this is one way of doing a proof, right? So in this section of the course, I don't expect any two students to always have the same proof, right? And I should not see that, because proof writing involves intuition and everyone has a different style. Okay, so let's move on to more proofs now. So all of these will be for your self-reading, right? How to disprove and stuff like that. This was already covered in the previous section, right? With the quantifiers, right? And it is proved by counterexample as well. So we want to talk about something called a proof by using the method. So this is another method. So we are speaking about different methods. So we want to use the method of something called exhaustion, right? To prove the following statement. For all n that belongs to Z, right? Instead of integers, if n is even and n is restricted between 4 and 26 inclusive, then n can be written as a sum of two prime numbers. So by its name alone, exhaustion, right? We can immediately see that we have to do exactly that. It's going to be a long and tedious process, as you will see in the, I believe it is the third or fourth tutorial sheet. There is a question exhaustion, and it's exactly that. We have to do a similar process here. So if n is even, so we have to look at even integers between 4 and 26 inclusive. So let's start with 4. 4 is even, right? Obviously, we'll have to end at 26. So we put 26 here. Then n can be written as the sum of two prime numbers. So just pick two prime numbers and do them for all. So go for 4, then do 6. 6 is even, and then take all of them before 26 and just ensure that these are all prime numbers. So 2, we have 3 plus 5, 5, etc., etc. Right? And you can go through this by pausing the video. This was also covered in the last section. And now we reach to the method of direct proof. And we have a nice step-by-step process here. So the first step here is that we express a statement to be proved in the form for all x inside whatever our domain is, right? If depending on how the proof is written, right? If p of x, then q of x, right? And we are familiar with this notation here, if p then q, because we did that in the first section of the course. So we start the proof by supposing x is a particular but arbitrarily chosen element of D, and this is good, right? So this means that there are different ways I can approach the beginning of this, for which the hypothesis is true. This is sometimes abbreviated as suppose x is inside some set D or whatever, and then P of x, right? And we show the conclusion is true by using definitions, which is what we had to learn at the beginning, which is why I said we have to learn them word for word. Previously established results and the rules of logical inference. This implies that you can have a statement at the beginning here, take that statement which you suppose, right? So we suppose something, then recall some definitions and some established results that we have. That's why I mentioned things like theorems and corollaries and stuff like that. And then use the logical rules of logical inference, right, to reach some conclusion. So here's an example. Prove that the sum of any two even integers is even. Okay, so whenever you are presented with a statement to be proved, it's a good idea to ask yourself whether you believe it to be true. Meaning that you have to make a judgment call here. When you are given the statement, does it sound logically accurate in your mind? And when you think about the statement and when you read the statement, something should be clicking in your brain that is telling you, hey, I have an idea about how I want to start this proof, where I want to go, or at least I'm able to see in my mind how I'm going to end up at some conclusion here, right? So those are some of the things that we have to think about. So in this case, you might imagine some pairs of even integers. Because we're thinking about even integers, our mind should immediately go to things like this and mentally check that their sums are even. You can write it out as well, right? That will help to boost your confidence when proofwriting. However, since you cannot possibly check all pairs, so that is impossible to do, of even numbers, we cannot know for sure that the statement is true. However, to prove the statement generally, we need to show that no matter what even integers are given, their sum is also even. So we need to have a general statement here, which is why we chose 2r and 2s. And then when we have that, we can say, well, this is of the form of some even integers. Then we can formally restate it like we did here. For all integers m and n, if m and n are even, then m plus n is even. So this is one of the most important statements right here. Then when we have established that, we can start by saying, suppose m and n are particular but arbitrarily chosen integers that are even. From that, we can then use the definitions and some logic and then prove that. So then ask yourself, what conclusion do I need to show in order to complete this proof here? We need to show that m plus n is even. So I started with m plus m is even. So this is my supposition. And then I have to show this. So this is the important question. How do I get from the starting point to the conclusion? Since both of these involve the term even integer, we must use the definitions of the term. So thus, we must know these definitions by memory. So we can then use that definition and then infer that it follows from the definition that m and n are even, which equals twice some integer. We don't need to take an example and then prove 2 plus something and something. That is an example. In a proof, we are proving in a general sense, right? So that is how we would handle a direct proof. Of course, this is as well an example for your self-reading. And we reach, so when we start to do proofs like what we did just now, right? So the sum of two even integers may be even, which is what we have here. Then we can say, wait a minute, if that is true, is it true that the product of two integers, even integers, is even? What about the product of two odd integers? And questions like this start to arise. And then we start to prove more and more again. When that happens, then we get a set of results like our theorems, which we spoke about at the beginning of the course, right? And these are factual statements. So now, to prove even more complicated statements, we can use these theorems here. So it's good to know these list of theorems. The sum of any two even integers is even. Okay? And this is very important. So this proof is just like, to some extent, the one previously done, right? The difference here being that we did some algebra here, right? Which I know everyone can do. So I'm going to just leave this up here so you can pause for your self-reading. And then we'll come to here. So all that is important, but we need to understand the methodology of how we prove, right? If you can get that down, then proof writing becomes much easier. So when we are given something like a question, like prove something, prove X, then we copy the statement of the theorem to be proved on the paper. So write it down. Just like the definitions, what you need to know, write them down, write them over and over again. That's the only way that you will remember them, right? Clearly mark the beginning of your proof with the word proof. So we need to write the word proof itself, right? And make your proof self-contained, right? So you don't want to overexert yourself and start to write a bunch of nonsense and stuff like that, right? We want to have clear logical steps like we had over here. a formal restatement, right? And then we have a clear starting point and a clear definition that we use and a clear ending. Okay? Then write your proof in complete, grammatically correct sentences. Right? So that is very, very, very important. Of course, I left out from before. If you want to include some statements in your proof that you want to use later on, that is fine as well. Right? In fact, I encourage you to do that. Right? So that it can help solidify your proof, right? As a good, strong proof. Keep your reader informed about the status of each statement in your proof. So don't bore the reader by saying the same thing over and over again. So just like we did in the previous proof, where we said m and n are integers, and then we went straight to another proof, and then we use the definition. So each line of your proof must be clear. So give a reason for each assertion in your proof. So this is very important. If you are using a certain theorem or result or whatever like that, we need to state it, right? When I say state it here, I don't mean state hence by theorem 2.1.1 or something like that. I mean literally write out the theorem. So for example, before we had the sum of any two even integers is even. So if we had to use that again, then we need to put in brackets since the sum of any two even integers is even, right? And we need to give reasons for each line where it is not clear, right? This helps to convince the examiner or the person that is reading your proof that you understand exactly what's going on. Include the little words and phrases that make your logic of your arguments clear, right? So when writing a mathematical argument, especially a proof, indicate how each sentence is related to the previous one. So like using these connective words here like then, thus, and so, hence, etc. So when we write something and then we write since the sum of two even integers is even, then we can write consequently, we can write a line where we actually perform that operation. So that is an example where we could use the word consequently, right? So if a sentence expresses a new thought or fact that does not follow as an immediate consequence of the preceding statement, but is needed for a later part of the proof, we then use words like observe that or note that, right? So we're going to keep it there as a side point. Maybe you want to label it, maybe label the line or the expression as the equation star one or something like that. And then we could recall it at some point in time. Then we're going to display equations and inequalities. So we need to have some statements here to back up all our arguments from before. And then we have our conclusion, right? So these are some helpful proof writing tips. So all of these are, so this is what I was speaking about at the beginning, variations among proofs. So I don't expect any two students here to actually have the same exact proof word for word, okay? So here's some common mistakes. Arguing from examples. So like I said in the beginning, you see, when we are proving the one with the integers, I said an example is not a proof, right? If you want to give an example at the beginning, that's okay, right? Just to start your proof or just to show that maybe it works for a base case like we have to do in induction or something like that. That's fine. But we cannot use an example and then say consequently from the above example. That is not how that works, right? We need to have some sort of expression here in order to have a general sense of what is going on, right? Because like for the example with the pairs, we can't go and find all the pairs. There'll be an infinite number of pairs, but we can't do that. So we need to have a general statement that represents our what is to be proven statement, right? So don't argue from examples. Using the same letter to mean two different things. So don't use star one and star one again. Label it as something else, star two. Don't jump to conclusions. So if you have to go from one step to the next, we need to justify that. Circular reasoning, right? So give reasonings for whichever step that you are doing. confusion between what is known and what is still to be shown. So don't, if you're using the fact that the sum of two even integers is even, don't go and try to prove that in the middle of whatever you are actually proving, right? If you're using it, then use it, right? But don't go and reprove anything inside there that doesn't have any effect on what is our conclusion. And use any rather than some. So there are a few situations in which the words any and some can be used interchangeably, right? So we'll get to an example at some point in time. So you see, some at some point in time, and then we'll speak about that. Misuse of the word if, right? So be careful. So all these are very important because we need our proofs to be grammatically correct, have proper sentence construction, right? So we cannot use the word if something and then we were given it in our statement. So perhaps we were given a statement and we were given a restriction between some even integers or something like that. Then we can't go any proof and said, well, if or maybe or something like that. That was already given. So we can't use it like that. Right? So all of these here now are for yourself reading, as well as this last example here, which shows a nice graphic here of what is the domain, what is the hypothesis, and what is the conclusion, right? Not, I mean, of course, not all our statements which we are asked to be proved will look as nice and easy as this, right? But it's a good starting point so that we know exactly how to begin our proof writing journey, right? So you can read this on your own time. Every complete bipartite graph is connected. So we actually need to know before what is a complete, what's a bipartite graph, and what it means for a graph to be connected, right? If we are asked to prove something like this. Of course, our type of proofs will be restricted to some extent or to a large extent with respect to our definitions that we are we have in this section of the course. So like at the beginning where we had our integers, so of course I will ask something to prove involving even and odd integers, etc., because those are the definitions that we already know, right? But this here, this example is just to illustrate how we break up these statements. Okay, and this will also be for your reading. So the word conjecture comes here, and we spoke about what a conjecture is at the beginning, which is it's a good thing that I mentioned it, right? But we don't really need to go into too much detail with the conjectures, right? At least in this part of the course, because we just need to know what it is. And so all of this you can read on your own time. Okay, so that brings us to the end of 4.1. In the other sections and the other videos after this, we'll continue with some more proof writing. I will go into some more details using different definitions, which will expand the types of statements that we are asked to prove.